Hi, and welcome to Chapter 7. This is series parallel circuits. This is a lot of information you should already know because it's just a combination of really chapters 5 and 6. In a lot of courses, there's no separate uh, chapter or separate look at series parallel circuits because it's really just a combination of things you already know. So, I'm not going to dig in a lot into some of these topics in this chapter, and I'm going to skip a few of the topics, um, but I'm going to go over several things. And like I said, a lot of it is should really be a review of things you should already know about series circuits and parallel circuits. Okay, so we're going to start with something really simple, and this is an idea of how do you approach when you see a circuit like that looks like this, right? What's the best way of attacking this kind of circuits? The book introduces two different ways, but really when you look at it, those two ways are so similar that once you start really solving circuits, you don't really make a difference into which approach you're going to be using. You just use whatever is more convenient, as you'll see. But the first one is called the reduce and return approach. And it's really just looking at, if you look at the circuit, for example, looking at the far end of the circuit, the right-hand side, and start kind of making it smaller and smaller and smaller until it becomes a simpler circuit like you see here from A to E, right? That's the idea, to approach it, to reduce it as much as possible, and to look for what you're looking for. Right? So the best way of seeing this is by looking at an example, right? So if we look at this example 7.1, the really important thing is that you really start recognizing what's in series and what's in parallel, okay? It's always a good idea, like I said, when you look at a circuit like this, to start from the right-hand side, going towards the left, okay? It's not the only way, but it's a good approach. And if you look at this circuit, right, you should, again, before you even start analyzing what you need, because in this example, they want current I3, right? That's what the current they want. But your first approach should really be understanding what's really in parallel and what's really in series. Well, it's kind of obvious here, right? I hope by this time that these two, the 12 and the 6, are in parallel, right? They share the top node, they share the load node, right? So the voltages across each of one of them is the same, right? So I can start by combining these two resistances. So that since they're in parallel, right? And you know already, that's what I'm saying. This is really a review with things you already know, okay? So I'm not gonna go over the little details. So when you combine these two, you can use the shortcut approach, which is what? Multiply the two, divide by the sum. So it's 12 divided by 12 times 6 divided by 18, which gives you a 4 kilo ohm resistance. So the circuit becomes this now, right? It becomes a 4 kilo ohm resistance, which now is in series with the 2 kilo ohm resistance, right? So in this approach, if we combine these two resistors, you get a 6 kilo ohm resistance, and that will give you the current coming out of the source, right? Again, nothing new, and you should really know this. So if you do that and apply Ohm's law, you'll have 54 volts divided into 6 kilo ohms, gives you 9 milliamps, right? So now you know, based on this second circuit, that the current coming out of the source, right? If you can reference now the top circuit, the current coming out of the source is 9 milliamps. So what you know now is that the 9 milliamps coming out of the source are going to go through the 2 kilo ohm, and when it gets to this node, it's going to split. Some of it is going to go through R2, some of it is going to go through R3. But you're interested in finding what I3 is. So to do that, you can simply use current division, right? Why? Because now you know that the current coming into this node is 9 milliamp. So if you use current division, right, then this current I3 right? If we use the shortcut method for two resistances, this current I3 will be equal to the opposite resistance, 12, divided by the sum of the two resistors. Remember, this only applies for when you have two resistors in parallel. So again, it's the opposite resistance divided by the sum times the current that comes in, or the current that's splitting, which is 9 milliamps. So that's what you have right here, right? The opposite resistance, 12, divided by the sum of the two times 9 milliamps, and that will give you this current at 6 milliamps. Okay, so, right, nothing really new here. We just use what we already knew from the previous chapters. All right, let's look at another one here real quick. And on this one, they want to find out, on example 7.2, the currents I4, IS, and V2. So I4 is this current, IS is the source current, and V2 is the voltage across these 2 points. So it's really the voltage across R3, which is really the voltage across R2, right? They're in parallel. Again, make sure you're recognizing that you're really being comfortable recognizing what's in series and what's in parallel. So in this circuit, obviously, you only have one resistor on this side, but this resistance R1 will be in series with the combination of R2 and R3. R2 and R3 are in parallel, but if you combine them, that combination will be in series with R1. So R1 plus R2 is in parallel with R4, right? And that's really all you need to know. But you notice a few things also, that the voltage across R4, and again, that's what you should know from previous chapters. The voltage across R4 is 12 volts, right? From here to here. And the voltage from here to the bottom is also 12 volts, right? Because there's nothing, see, they all share the same two nodes at the top, same two nodes at the bottom. Or the same node actually at the top and the same node at the bottom. So if we combine R2 and R3, again, the shortcut method, 18 times 2 over 18 plus 2 gives you a 1.8 kilo ohm resistance. And if you were to draw that circuit, this circuit here, it becomes this one now, right? Okay. So, so now the question is, well, how do I find I4? Well, I4, I couldn't find I4 from the very beginning. I didn't need to combine anything here to find I4. Why? Because I already know that the voltage across R4 is 12 volts, right? And I know the resistance. So I didn't really need it to deal with this side of the circuit to find I4 specifically. So I4 is simply 12 volts divided into 8.2 kilo ohms, and that gives you 1.46 milliamps, right? Now, to find V2, which is this voltage here, that will help if I reduce the circuit like I have it here, right? And if you notice here, now, there's more than one way you can find that voltage, but an easy, quick way is really to use voltage division. Why? Because if you notice again, the voltage from this node to that node is 12 volts, right? So if I use voltage division, it's saying that the voltage across R1 plus the voltage across R2 is equal to 12 volts. So if I use voltage division, again, I'll say, well, V2, that's what it's critical that you know how to use these rules, okay? The voltage division and current division rules. So voltage division tells me that this voltage V2 will be equal to this resistance, right, the adjacent one, excuse me, over the sum of the two resistors times the voltage that splits, which is 12 volts, right? So it's this resistance over the sum times the voltage, from between the two, and that will give me 2.51 volts. So again, like I said, is there any other way? The other ways you can find the values you're looking for, but those are really the fastest way, and I would encourage you to look into this example a little further, so you can also see the other ways that you can find the voltages and the current. And importantly, with this example here, you notice here this is the same example, right? And even though we this late in the semester, I noticed that some of you are still struggling to measure current. Okay, still a struggle, and you should really, by this point, you should really be comfortable measuring current. And if you're not, again, take a look at this example, right? This is how you will measure the voltage. Obviously, you don't have to disconnect anything. But to measure the current, you will have to disconnect this point and in its place, put the meter, right? So the meter is in series with this resistance, right? See, notice the difference, right? And that's how you will do it if you were to set up the circuit on a proto board. All right, so that's the reduce and return approach that is called, okay? The next one is called the block diagram approach, which again, I found the two methods really very similar. And at some point, especially in my course, I'm not going to ask you to use one method specifically or the other. I might just find something, a current or a voltage or power, whatever, and use the method that you think, applies the best and you can feel more comfortable using it. But in this approach, the idea is that you look at blocks in the circuit, right? Specific blocks. For example, if you look at this circuit here, right? You choose, for instance, to look at a portion of a circuit at a time, and this is indicated by this blue rectangles, and then you reduce whatever you can based on those sections of the circuit you have chosen, right? For example, let's look at this example 7.3, right? It says, find the currents and voltages of this circuit. Well, again, what they chosen to do is to look at the different sections, if you will, of the circuits, right? You have a section here that has two series resistors, and you have a section here that have two parallel resistors. And what they've done is, and of course this other section here that will be in series with whatever you have on this other side. And what they've chosen to do is just to reduce the individual blocks, if you will. They have a block B and C, right? So if you do that, obviously you'll have with block B, which is this one, you have these two resistors in parallel. So the equivalent resistance for that block, it will be 2, right? Again, if you remember those nice, useful rules that you should by now, you remember that if you have two resistors in parallel of the same value, the equivalent resistance is half of one of the resistors. So in this case, it's 2, right? In other words, it's 4 times 4 divided by 8, and gives you 2. So this block gives you a 2 ohm resistance, and this one will also give you a 2 ohm resistance, because when you add 1.5 to 1/2, you get a resistance for C of 2 ohms. And then there you have it. You reduce the circuit from this to this by choosing certain blocks. And then the rest is the same, right? But, you start finding what you need. In this case, you could start by finding the source current, right? Since you already know this is 2 and this is 2, right? Again, if you use that rule of 2 resistors in parallel with the same value, the combined resistance will be 1, right? So you will have 4 plus 1 is 5 ohms, and then the total current using Ohm's law will be 10 divided into 2, or 5 amps. I'm sorry, 10 divided into 5, or 2 amps, right? Because again, if this is 2 and 2, the combined resistance will be 1, and you have 4 plus 1, right? So the total resistance in this circuit will be 5 ohms. So by Ohm's law, 10 divided into 5 will give you 2 amps, and that's it. And the rest, again, will be easy, right? Once you know the source current, you can easily find the individual currents in the circuit. In this case, for instance, since the current coming out of the source is 2 amps, you know that, right? Coming into this node. Since the resistors are the same value, the currents are going to be the same in this specific case because the resistances are the same. So if you have 2 amps coming into this node, you're going to get 1 amp here, 1 amp there. So there you go. You got all your resistances in the circuit. Okay. And notice that on these examples, I'm skipping a few details, and my goal is that you fill in those details when you're solving, like solving for the individual voltages. Because again, this is really a review of things you should already know. Okay, we're just looking in the general case. So I'm gonna let you fill in the gaps, and you should really study these examples on your own. And not just study them by doing them. Don't look at the solutions like I told you before. Look at the problem. See if you can find what they're looking for, and then look at the solution, right? Another example, again, I'm not going to solve everything here, but the approach here is that they're looking, again, at blocks in the circuit, right? And how you decide what's a good block, there's really no real rule. It's just a matter of what is convenient for the specific circuit. In this case, normally you look for branches in the circuit, right? Like in this case, you have this branch, this one, and this one. On this branch, you only have resistor R6 by itself. On this one, though, you can start by combining those resistors, and on this one, you can combine those resistors. The idea is that you're making the circuit simpler, right? So notice here that in this block B, you have this resistor R3 in series with a parallel combination of R4 and R5, right? So these two are in parallel. So the combined resistance of these two will be 6 times 3 divided by 9, right? And then for R3, obviously, you just add that value to that combined resistance. So 6 times 3 divided by 9 give you 2. 2 plus 4 give you 6. So for block B, for this block, the total resistance can be replaced by just a 6 ohm resistance, as you can see here, right? That block becomes this. And this one doesn't change, but you can do the same thing for this one where you have two resistors in parallel, the 9 and the 6. So again, 9 times 6 divided by 15 gives you 3.6 ohms. So this block A becomes this. And now again, you have a more simpler circuit that you can manage, again, like we did in the other ones, right? So now you can find whatever is needed. They want to know all the voltages. They want to know all the currents. Again, you can start by doing things like finding the total current, combine these two, the 6 and the 3. The 6 and the 3 gives you a 6 ohm resistance, right? And then you add 3.6 to that. So the total resistance, the 6 and the 3 gives you a 2 ohm resistance. I think that's what I said, a 2 ohm resistance, right? 6 times 3, 18 divided by 9 gives you a 2 ohm resistance. And you add that to the 3.6, so the total resistance now is 5.6 ohms. And then using Ohm's law, the current will be 16.8 divided by 5.6, which gives you a total current of 3 amps. Again, now that you know the current is 3 amps, you can use current division to find IB and IC. And again, I'm going to leave that for you to really do it on your own, right? Try to find IB and IC by using current division, like we did before. And once if you know the currents, then you know the voltages by Ohm's law, right? So, and this is in the rest of the example here. But I'm going to leave you finish that up, okay? But just again, just showing you the approach on how you start solving this kind of problems. All right, I'm not going to go over section 7.5. This is really not a section. It's just it's just more problems of the same, right? I'm maybe going to show you a couple of examples, things that you may be able to see. Again, look at this example here, right? Let's say if it says find the currents, they want to know, for instance, this current I2 and this current I4. Well, a good approach at this point might be, and it's not always the best approach, but it's a first good approach to reduce the entire circuit as much as possible, right? So if we reduce this block, if you will, of 3 resistors into one, and this block of 2 resistors into one resistance also, then what you will get is 6, 6, and 2 in parallel, right? So if you reduce 6, 6, and 2 in parallel, you get a 1.2 ohm resistance. Again, that's something I encourage you to do it on your own and do it and find it without looking at the solution. And for the 6, for the 8 and the 12, you do the same thing, right? You multiply 8 times 12 divided by 20, and this will become a 4.8 ohm resistance, right? And then you find the total resistance, which becomes 6 ohms. With that, you can find the source current, 24 divided into 6, gives you 4 amps. And now if you go back to your circuit, you notice it's really the same, we're using the same techniques, voltage division, current division, Ohm's law, right? Combination of resistors in series, combination of resistors in parallel. It's nothing new here. But in this case, by doing this reduction of the circuit, you found the total current. And if you look at the circuit here, right? So now that you know the total current, what you know is that this current coming out of the source is going to split into 3 different currents. A current that goes through R1, a current that goes through R2, and a current that goes through R3. How do I find I2? Again, there's more than one way of doing that. But if you notice here, in this example, right, you know the voltage, for example, V1, you can find that voltage. Why? Well, you already know that that the combined resistance here is 1.2, isn't it? Right? And as you know, in a parallel combination, the voltages across each of those resistors is the same, right? So since you already know that this resistance is 1.2 ohms, and you just found out that the total current coming out of that source is 1.2 ohms, and the total current coming out is 4 amps, then by Ohm's law, right? Notice here, by Ohm's law, the voltage drop across this combined resistance or total resistance is going to be simply 4 times 1.2 ohms. And the voltage drop across here is going to be, again, 4 times 4.8 ohms, right? Ohm's law. And once you know that, then, once you find the voltage, once you find the current and you know the voltage, right? This I2 is also easy to find out by Ohm's law. The voltage across here is also whatever we found V1, the product, right, by Ohm's law, 4.8. So this voltage is 4.8 here, 4.8 here, 4.8 here. By Ohm's law, I can find I2 because I know this value of resistance, right? And the same applies for V5. I know V5, so I should know what I4 is by Ohm's law. Okay? All right, so really nothing totally new. It's just the way the circuits look. They look a little more complicated because we now combine the 2 cases, but the approach is still the same. So I'm going to leave this other ones for you to really review. Let me just go over this one because it kind of has that notation, graphic notation that it gives some of you still problems, even though this is from one of the chapters we already discussed. But so we're given this problem here in figure 722. Okay, and I want to know what's the voltage V1, well, and the V2 and the current I. Well, first of all, make sure you recognize what they mean by those voltages. Okay, that you are sure of what they're looking for. V1 then is the voltage across the 6 ohm resistance. V2 is also the voltage across this 6 ohm resistance, R4. V1 is the voltage across R1. V2 is the voltage across R4. I, that A1, is the current coming out of node A, as you notice here, right? The current coming out of node A, right? It's important that you define those voltages, those currents, based on your circuit, so that you know you're going in the correct direction to solve the problem. All right. So notice here that this node A, everything is connected to node A. You notice that, right? The source, you can start by the source, right? This source. The negative of these two sources, you notice here, right? These two little circles represent sources, right? The this side of node A is connected to the negative of this battery or source, right? This part of node A is connected to one side of R1, but the other side of R1 is connected to the positive of the 18-volt source, right? This part of node A is connected to one side of the resistance R4, and the other side of the resistance is grounded. And this side of node A is connected to resistor R3, which is in series with R5, which is then grounded, right? So you notice here that every one of those points, right, this resistor, this source, and this resistor, they're all connected to a single node A. So you don't need to, but if it helps you visualize the problem better, you can redraw the circuit to look like this. And what you notice here is that this is something similar to what you will have on a protoboard, right? You will connect R3, one side of R3 to A, right? And if you follow, it's the same thing. R3, one side of R3 to A, one side of R4 to 6, right? Follow that. The negative of the 6-volt battery to A, the negative of the 6-volt battery to A, one side of R1 to 6, right? All right. So this represents, you know, like the 5 little holes in your protoboard. And on the other side, you'll notice that R5 or R2, I'm sorry, is connected to ground on one side. The other side of R4 is grounded. The positive of this source will be grounded. We know that. And the negative of this source will be grounded. So this, knowing how to go from one of the circuits to the other one is really critical. So make sure you spend as much time as needed making sure you understand how to go from one to the other. If possible, just don't even look at this side and try to redraw it, you know, from this point, and try to redraw it to make it look like it's comfortable for you, and then look at how this may look like in here. Okay. And now once you have it like that, well, they want to know what is voltage V1 and V2 and the current I, right? This current. And you notice again, it's important that when you redraw your circuit, you don't lose track of what you're looking for. That's why I said at the beginning, it's important that you recognize what is it that you're looking for. Not just saying, oh, I'm looking for V1. Well, what exactly is V1? What exactly is V2? Well, V1 is the voltage across R1. And notice here that in the redraw circuit, V1 is the voltage across R1. V2 is the voltage across R4, right? Across R4, okay? And the current that I'm looking for is the current coming out of node A going into the negative of the source, right? And you notice that's the same current here, right? Coming into node, coming out of node A, going into the negative of the source. So it's coming out of the positive of the source, right? You notice how this is important, right? And obviously, immediately you'll see, well, if this is in parallel with this, and with this, then immediately you know that V2 is the voltage across this 6-volt source, which is the same voltage. The only point is that the polarities are reversed, so that means that voltage V2 is -6 volts. It's the equivalent if you put a meter with the positive lead here and the negative lead at the bottom of the ground, and you will measure, in this case, minus 6 volts, right? And then the rest is easy, the same thing. So now that you know, if you know this voltage, and if you know this voltage, you can use KVL to find V1, right? You do a little KVL around this loop, and if you do that, you can say, well, V1 is equal to, you know, because you have, if you remember, if you do a KVL where you add the sum of the voltage rises equal to the sum of the voltage drops, right? If you start, for instance, from node A across R1, you have a voltage gain, right, of V1. So that voltage gain of V1 is going to be equal to the sum of these two voltages, right? Because these two voltages from plus to minus, they add up together. So V1 is the sum of 18 plus 6, right? KVL. Again, nothing new here, but important that you understand how we get in that V1 is 24 volts by just looking at KVL. And then to find I1, well, I1 can be easily found if you look at, if we apply KCL at node A. Oh, there's no I1, they want to know what I is, right? Which is this current here. So if you look at this current, if you look at this in terms of KCL, right? This big node here, right? Some of the currents going into the node, some of the currents coming out of the node. So, well, I3 is the same current going through these two resistors into node A. I2 is the current through R4 going into node A. This I is coming out of node A, but this I1 is coming into node A. So again, critical KCL, that you understand what's coming in, what's coming out, currents, and add them together, right? You add the currents coming in equals to the addition of the currents coming out. So in this example, in this problem, you have I3 plus I2 plus I1, because they're all coming into the node, equal to I, because it's the one coming out of the node. And there you have it, right? Okay. Don't worry about this one. This shows a transistor. We're not dealing with transistors at all. So this, in this example, don't even, don't bother to look at this particular example. This one you may want to do. I'm going to leave it again as an exercise. What they've done here again, you don't have to again, but what they've done is they redrew the circuit to make it look a little more friendly looking, so that you can, maybe analyze it a little better that way. But all they've done here is, if you look, from here to here, is that they combine the resistors in series on this side. See, these two are in series, right? And remember, because the current going through this resistance has no other way to go but through this R9 resistance. So these two are in series, and what's they've done? They combine these two, 6 plus 3 equals 9. And obviously those two will be in parallel, the 9 and the 9. And on this left-hand side, the same thing. These resistors are in series. So they added those three resistors and you get a 24. So that 24 will be in parallel with this other 24. And see how easy it is now, because you got a 9 and a 9, a 24 and a 24. And really, it becomes a simpler circuit. All right, so again, I'm going to leave this one for you to study and finish and take a look. Okay. Same for this one. Again, like I said, this is really a review. So it's really important that you really study those examples, applying what you already know. Okay, the other type of circuit we're going to be looking at is called a ladder network. It's called a ladder network because it looks sort of like the rungs of a ladder, right? If you look at this circuit, right, a lot of circuits look like this. A lot of connections. The way we connect circuits look like that, like houses and elements or devices within a house. They're connected in this fashion a lot of times. So it's a common way of connecting networks, and that's why they call it a ladder network. And again, there are a couple of ways that you can deal with ladder networks like this. There's really not a whole difference between the two, so let's just dig into one example so you can see how it's done. That is basically the same way you did before with the ladder. I mean, with the block diagram and the reduce and return approach. So in this case, right, if you look at the circuit, okay, you can start by combining when you can combine, right? If you combine these two, you get a resistance in series, right? The 1 and the 2, right? And you can do it, right? At one point, it'll be nice if you can do this in your head, right? At least some portions of it. Because what happens, right? If you combine the 1 and the 2, you get a 3, right? So that 3 will be in parallel with the 6. Well, 6 and 3, right? 6 times 3 is 18 divided into 6 plus 3, which is 9. So 18 divided into 9 gives you 2. So these 4 resistors become a 2 ohm resistance. Okay, 2 ohm resistance. That 2 ohm resistance will be in series with a 4 ohm, so now you got a 6. So from here to here, everything is 6. That 6 will be in parallel with this 6. See? If you have a 6 and a 6 in parallel, it becomes a 3. All right? Remember that? And so now all of these resistors really become a 3 ohm resistor, which is simply be in series with a 5 ohm resistance, and so the total resistance is 8 ohms. Okay? So again, maybe you're not 100% comfortable doing it this way now, but eventually try to practice. Practice it that way. But you can do it one step at a time, right? So you can go series, combine them, redraw the circuit, then combine those two again, and so forth, until you get a total resistance. And if you know the total resistance, then you know the total current, which will be 240 volts divided into 8 ohms, gives you a total of 30 amp current. And that's what they've done here. See? So you can do it one step at a time, but practice. Try to do it with just that approach. At least try to understand where you're going by taking an approach of what you're going to combine and so forth. The other approach is that they assign a letter symbol to the last branch and then work back through the network of the source. So they just, like in this case, they say, well, if you look at the circuit, again, this is another approach, right? If you look at the circuit, you say, well, if I want to know what I6 is, I know that I6 is going to be equal to the voltage V4, whatever that voltage is, divided by the sum of those two resistors, right? I don't know what a V4 is, right? But you're going to go back. You're going to go back in the circuit towards the left. Well, again, I don't know what V4 is, but I have an expression for I6 in terms of V4, right? But now he said, well, I4 is going to be equal to V4 divided into 6, right? See that? So, and now you have an expression for V4 that you can put into this formula and keep going that way, keep going that way, keep going that way until you hit the beginning of the circuit, and then you find what you're looking for by plugging in all the unknowns. Now this method, I don't really like it that much because you're dealing with an unknown from the very beginning, and then it's easier to make a mistake. But still, I like you to go through it and understand what's going on. But I would rather recommend the first approach, okay, which is less prone to errors. But you see that it's the same idea, right? You just start combining whatever you can combine, apply the methods that you already know, voltage, KVL, KCL, voltage division, current division, and so forth. All right. This section, I'm only going to mention one thing, and this is what I mentioned also in the lab. Things are different when you have a circuit, what is called no load, and you have a load to it. For example, what that means is that, remember what I always said in the lab, if you're looking to have a voltage in the circuit, in the protoboard, don't always trust what you see in the power supply display. Because the power supply display tells you the voltage that is coming out of that source. But the moment we put a resistor, or what's called a load, across that source, the voltage is going to change. And that's why you always have to rely on your meters to give you the correct voltage, not necessarily on the display of the voltage source. Okay? Because once you put a load, once you put a resistance across the circuit, the system is going to change the conditions. The loading down the system is the process of introducing elements that will draw current from the systems. The heavier the current, the greater will be the loading effect. So circuits under no load conditions are going to draw less current than circuits under load conditions when we put something across it. Okay. I'm not going to go into that. I'm just going to it's one of those sections. I'm not going to go into a lot of details, but I just want you to get the idea that when you put a load across the circuit, then you're drawing more current, okay? And the characteristics of your source are going to change, okay? But let's try this circuit, because this example 712. And apply some of those concepts, because they put an important twist here about the 2-watt resistance, and I want you to understand that concept if you haven't already. Let's look at this example. It says find R1, R2, R3 for the voltage divided supply in this figure. Can 2-watt resistors be used in this design? Well, this is the deal, right? This is normally called, and look at how they have this blue block here, because this is what is normally called a voltage divider circuit. Why? Because if you start by looking at the circuit, right, this voltage from A to ground, VA, from A to ground is 120 volts. Okay. Well, how do I know the voltage from B to ground is 100 volts? How do I know the voltage from C to ground is 60 volts? Right? I don't know. Right? I know that the voltage from A to ground is 120 volts, because it's it's this node and that node share the same nodes with the power supply. So VA is obviously 120 volts. But if you notice here, if you use voltage division, then you can say, well, the voltage B to ground is going to be equal to 50, this resistance, divided by 60, right? 50 plus 10. So this voltage here is going to be, again, 50 divided by 60 times 120, and that should give you 100 volts. The same thing here for VC. VC is going to be 30, right, divided by 60 times 120. See? So 60, I'm sorry, not 60. This voltage here is going to be 30, right? This resistance divided by the total resistance, which is 60, right? Times 120. So 30 divided by 60 gives you 1/2. 120 times 1/2 gives you 60. See? So using voltage is a voltage divider circuit, as you can see, right? I hope that's clear, right? Make sure that you understand that. So the voltage from C to ground is 60. The voltage from B to ground is 100. The voltage from A to ground is 120, right? Don't be confused by that. Make sure you understand that. And you can use voltage division to corroborate it. So going back, it's a commonly used circuit. It's called a voltage divider supply circuit. So if we go back to our example here, right? We have, look at the block, the blue block box here is the same circuit that we had before. It's just the configuration is a little different, how they grounded this leg and the connections to the circuit. But this side of the circuit is basically the same, right? You have a power supply connected to 3 different resistors in series. Now, it could be more than 3, it could be 2, it could be 4, 5, whatever. The idea is still the same. But in this case, it says, well, find R1. What is the value R1 and R2 and R3 for this particular voltage divider? Okay, let's just deal with that right for now. Well, let's see what R3 is. R3 is first. You notice here that R3 is connected to a minus 12 volt supply, right? So V, because of the ground, look at the ground, right? So that tells me the reference, correct? So in this particular case, you notice that IS is given, right? The source current is given, it's 50 milliamps, right? So R3 by Ohm's law is going to be equal to the voltage across this resistance, right? The voltage across this resistance is 12 volts, right? If you put a meter from this node to this node, right? Well, in other words, from this node to ground, right? If you put my positive here and my negative at ground, I'm going to measure 12 volts, okay? All right? So I have 12 volts in the current, as you can see, right? It's coming out of that node through this voltage supply. It's 50 milliamps. So this resistance, then I know the voltage across it, I know the current coming through it, and that will give me a resistance of 240 ohms. Okay. Again, a very interesting circuit, right? But make sure you see the connections and how we get that resistance. Well, if you calculate the power absorbed by that resistance, it's going to be, if you use the current, it's going to be the current square times the resistance, and that will give me a 0.6 watt a 0.6 watt resistance. So so the power absorbed by this resistance is 0.6 watts. If I use a 2 watt resistor, it can still tolerate the 0.6 watt, right? Because it's less than what this resistor is rated for. This resistor, when you see something like a resistor rated at a certain power, it tells you the maximum amount of power they can withstand. So in this example, it's saying if this resistor is rated at 2 watts, it's saying that it can withstand up to 2 watts of power. Well, in this case, we computed the power that the resistor absorbs as 0.6 watt, which is less than the rated value. So that means that it can withstand 0.6 watts because it's rated to withstand up to 2 watts. Okay, so for this one, it's okay. Now let's look at the other ones, right? For R1, I'm going to apply, and let's see if I can do this. Let's try this little trick in just 1 minute. I'm going to bring the circuit all right, and I think you can see that. I hope that our original circuit, right? So now we're looking for R1. What is R1? This one, right? R1. Well, now if I apply Kirchhoff's law, current law, to this node A, right? And this current is already given in the problem, right? So you can see that I have 50 milliamps going into node A. I have 20 milliamps coming out of node A also. And if I do my KCL, right, I don't know what this current is. I know what the current coming out of B is, right? So so I can find R1. the current through R1 because I know that one coming to here and the one coming out of here, right? So as you can see, if I look at the currents coming in, right, which is IS, and add it to the currents, or algebraically notation, right? Remember from KCL, right? If I add them algebraically with the signs in place, so coming in, I have 50. Coming out, I have IR1. Coming out, I have 20 milliamps. So applying KCL, this is my formula, right? Oops, where did it go? There we go, right? So make sure that you're clear how we got this here based on the direction of this current. And now that I have that, I can solve for IR1 because I know the other two currents. So IR1 is going to be equal to 30 milliamps. It kind of makes sense if you look at it, right? You have 50 coming in, and on one side you have 20 coming out. So the other one should be 30, right, to complement the 50. Right, that's what you got right here, right? So then R1 is simply going to be this voltage, right, divided by the resistance, by the current, by Ohm's law. This Ohm's law, right? This voltage divided by the current. Now, I found the current already, but I don't know what VR1 is. Well, I don't know what VR1 is, but I do know what the other voltages are. If you notice in the circuit, right, this voltage from A to ground, right, from A, look at the connections, from A to ground is the same voltage that is being read from this point to ground, right? So it's 60 volts. See how it's 60 volts? From A to ground is the same voltage on the right-hand side across RL1, the load 1, right? So VA is 60 volts, or VL1, we should say, is 60 volts. And then this voltage at B, VL2, this one here, is 20 volts, right? It's just that voltage. So the difference of voltage between A and B is 60 minus 20, which is what you have here. And that gives you your resistor R1. See? Now let's calculate the power absorbed by that resistance. As you already know the current, right? Let's use the current, IR squared times resistance R1, and it'll give you a power absorbed by R1 equal to 1.197 watts, which is less than the rated 2 watt resistance. So that one can be used also. And finally for R2, the same approach, right? Let's look at the currents. At point B, you have 10 milliamps coming out, right? And then you also have what 30. What is it? 30. Yeah, we already calculated this current, right? R1 through R1, we already calculated as 30 milliamps, right? And notice here, you don't even have to do KCL, but it's important that you do it as a practice so you can get this equation right here. Look, this equation. But you notice that this current through R1 goes into B and then splits, right? Some of it goes to RL2, some of it goes to R2. So if 10 out of 30 goes to this resistance, then you're going to get 20 on this side, right? Right away. But you can do the same thing by looking at the currents coming in plus the current coming out, which is this equation. So right away, that current is 20 milliamps. You know the voltage across R2 is 20 volts, right? They're in parallel. So now you have your resistor of 1 kilo ohm. If you apply the power formula, then you get the power absorbed by that resistor is 0.4 watts. It's less than 2 watts. So for all those cases, the power absorbed by each of the resistors is less than 2 watts. So we can use 2 watt resistors for the design. Okay? All right. Let's look at one using potentiometers. Now remember how a potentiometer works, a variable resistance, right? you have a resistance which has a total resistance, in this case is indicated by RT. Between these 2 points, that resistance doesn't change. But as you move the dial, right, remember we look at this example, if you move this dial, if you will, like in a volume knob, the resistors R1 and R2 are going to change. But the sum of R2 and R1 is always going to be RT. That's not going to change. But as in several ways, the way this is used is to get voltages that we want across some load, right? Because if you notice in this circuit, right, this is under no load conditions, right? I have no load attached to it. This is just the variable resistor tied to the power supply. But if I put a resistance across, right, from B to C, right, then I can then regulate what voltage I see across the load. Because if you notice that voltage across the load, if you use voltage division, it's going to be equal to whatever that resistance is times the voltage that splits added to the sum of the two, right? Which is this same expression here. Look, this resistance R1, or R prime, I should say, right? Because I'm looking for this voltage, right? This voltage is going to be equal to this resistance R prime. Well, this resistance R prime is the parallel combination of R1 and RL, right? That's what R prime represents. So by voltage division, this voltage is going to be equal to R prime divided by R prime plus R2 times the voltage that splits, right? So that's a typical use of potentiometers to regulate voltage. There's only a little rule that is used when adding a load like this to a pot, right? And the rule is that the resistance that you're adding to the load has to be much greater than the total resistance that you're using for the pot. So when hooking up a load to a potentiometer, be sure that the load resistance is much greater, far exceeds the maximum terminal resistance of the pot in order to have good control of the output voltage. If this rule is not followed, then this voltage, what it's saying is that if you don't follow that rule, then that voltage is not going to be well regulated. Okay, it's not going to give you a good voltage that you can use. And I'm going to leave this as an exercise for you to try it. In the case of where they chosen, this very low value of resistance compared to the pot, and then this very large value of resistance compared to the pot, and you'll see that the voltages are much better regulated. So I'm going to leave this for you to study on your own, and we're going to do an example to show you how it's done. Okay, so this is an example, and the example kind of summarizes what I just said and what the other page is saying, but I want you to understand why that is. But in the example, it's going to show you how that works, right? So in this case, it's saying, well, find the voltages V1 and V2 for this loaded potentiometer, right? Again, remember, the pot is a 10K pot, right? From here to here is 10K. So whenever you set the dial, right, the total resistance is not going to change, but the values of the top and the values at the bottom of that resistor are going to change. And you get two different values. In this case, it's set up so that you have 6 at the top, 4 at the bottom, right? You understand that point. And then you have two resistors attached in parallel to each of the legs of the potentiometer. So in this case, V1, if you look for V1 here, it's going to be equal to the voltage across. But first, let's look at it with, assume that there's no load, right? Assume that we don't have those 30K and 12K attached to the pot, right? And let's just look at what kind of voltages we will get across the pot itself, right? So let's forget to the loads at the moment. And so V1 will be 4 by voltage division, 4 divided by 10 times 120, and I'll give you 48 volts. V2 will be 6 divided by 10 times 120, or 72 volts, right? So that's under no load conditions, right? So if we now add the loads, right, to the pots, to the 2 points, we added a 30 and a 12, that's going to change because now you have 2 resistors in parallel. So now V1, right, and if we calculate those resistors, it'll be R1, this one will be 4 in parallel with 12, gives you 3 kilo ohms, and 6 in parallel with the 30 will give you 5 kilo ohms. So when we look at the voltages, now you'll have 3, because you have the parallel combination of those 2, divided by 8, because now it changed, because the parallel combination times 120 volts gives you 45 volts. And the same thing for V2, it'll be 5, because now you're looking at the parallel combination divided by 8 times 120, it'll give you 75 volts. So in this case, the ideal, because this is the ideal voltage, and the loaded voltage, when we added the load, are so close that we consider this a good design, right? In this case, you notice that the reason why the ideal voltages and the loaded voltages are the same is because we've chosen the values of the load resistors to be much greater, or greater than the values of the total value of the pot. Okay, so that's what shows you what it says before. All right, now let's look at the impact of shorts and opens in circuits, which is very important, right? I'm going to leave you to read this. Let's see. Well, let's see this example, just to see the impact of what happens if you have a short in the circuit. So we're looking for V1, V3 in this example, and then VAV. So V1, V3, VAB, and it says we're looking for those voltages and the source current, and we're going to compare to the levels obtained in example 7.7. Let's see, where's example 7.7? No, we got to go back. Let's go back. I don't remember what we're looking at 7.7. Well, that's really way at the beginning. Okay, there we go. So this is the same example, right? The difference is going to be, well, let's see. Let's see if there's any differences in the circuit itself. I'm going to keep this one. I'll bring it back in a moment. So let's go back to our example that we were looking at just now. This one. Okay, so oh, see what they've done? Let me reduce this a little bit. I think that's better. See what they've done? This is the example, the original example 7.7, and what they've done is they shorted this point from B to ground. They shorted that. See, they created a short. All right. And what they're saying is, well, let's see what the impact is of having that short in the circuit. So if we redraw the circuit, see what happens now is that this point B become a ground, right? And so that means that R1, right? If you notice, if you notice this top portion doesn't really change, right? R3 and R4 are not affected by that. But R1 is, and R2 is, because R1 is now grounded, and R2 is now grounded, see? So the circuit became this due to that short, because this point B is grounded, so R1 is connected to ground, one side obviously, and R2 is connected to ground on the other side, see? So that's what we have right now, because of that short. So now V1 is going to be, where's V1? V1 that they're looking for is here, right? So V1 is going to be the voltage across R5, right? But now, since it's grounded, it's right across, is right in parallel with the 6-volt source, except for the polarity. So V1 is going to be minus 6 volts. You notice that, right? Right away. If we apply Kirchhoff's law on the right-hand side of the circuit, well, obviously we apply, because we're looking for Vx, well, we can use Vx in this example to find the other voltages. So if you want to know what Vx is, you can quickly do a KVL right from the outside loop. See, if we go from ground around clockwise all the way back to ground, right? Again, from here all the way back to ground. And if we add the voltages gains plus the voltages drops using KVL, you'll get, well, if you start from the bottom here, the ground, and you go across this source, you have a voltage drop of 6 volts, or minus E1, plus another voltage drop of Vx, and a gain of E2. And that should all be equal to 0, right? This equation right here, very important, right? KVL again, right? That's what's critical, that you know KVL very well. And since we know E1 and E2, we can simply solve for Vx, and so happens that Vx is equal to 12 volts, right? By the way, you could have also figured that out by saying, well, Vx, because if you look at these two endpoints, right? At this point, this voltage is minus 6 volts, and at this point, this voltage is minus 18 volts. Vx is the difference of those two voltages, right? So Vx is minus 6 minus 18, or minus 6 plus 18, which gives you 12 volts. See? So that also checks. So whether you use Kirchhoff's law or you use the, the analogy of the two potential points, you're going to get the same value. And now if we use the voltage rule, you have, well, V3, which is this voltage, because now we know the voltage across these two resistors. V3 is going to be equal to 6 divided by 8 times Vx, or 9 volts. And if you apply Kirchhoff's voltage law again to the other, to V3, right, you also get this voltage here for VAB, because they're looking for VAB, this voltage across here, right? So now what they're saying is, okay, we found out what V3 is, right? We know what this voltage is, right? 6. So if I do a little KVL here, right, little KVL, that will give me VAB. So in other words, if you put a meter with a lead at A and a lead at B, that's your VAB. So really the difference, or the voltage AB, is the sum of these two voltages, V1 and V3, right? But since there happen to be negative, right, then you get a VAB of minus 15 volts. And so the currents can be easily found. I'm not going to go over how to find the currents. Again, you should, something that you should know. But the problem is showing you is that the difference from what we had in the previous example, right, to where we added that short from B to ground, the difference is in the voltages that you get, right? As we noticed before, see, this leg is not really impacted, so V3 remained the same. This leg wasn't impacted either, because you were measuring from A to this point B, which became ground. But some of the other measurements, some of the other voltages are impacted, okay? And so that's what's important, that you're aware of shorts or opens in the circuit, because it's going to impact areas in your circuit, and you should be aware of how to handle that. All right, this is another example of the same example, but in this case, they added an open, all right? And I'm going to leave that. I'm going to mention a few things, but I'm going to leave it as an exercise for you to do it. But you notice right away that if you measure in V1, right, Now it's saying, well, this is open, right? So resistors R1 and R2 are connected only at one point, okay? So they're only connected, you know, I'm sorry, R1 and R2 are now only connected at one point. So the circuit really looks like this, see? In other words, you can ignore R2 and R3 because in effect, you know, there's no current going through it, right? There's nothing going through it. It's like they're not connected, right? So it's that even though they're still physically in the circuit, they don't have any effect in the circuit, right? You notice that. And so this V1 is going to be 0 because you effectively have 0 current going through here, right? So that's, again, one of the effects. So see what happens by creating this open here? The circuit becomes this, right? And it changes the behavior of the circuit, right? So that's what this point is. And see how the values now change again from the example 7.7. The fact that you have shorts and opens in the circuit should really be taken into consideration to see how it's going to affect the results. All right, and I think that's all I have. I'm not going to go over this section 7.10. You can ignore that. But again, as you notice here, this chapter has really been a review, if you will, putting everything together that you already know in order to solve more complicated circuits, right? The next chapter is going to really introduce new techniques, still based on what you should already know. It's still based on Ohm's law, KCL, KVL, and so forth. But it's going to introduce some techniques that can be used to handle more complicated circuits. As you notice here, the more we get into this chapters, the more complicated the circuits get. So please review these examples, review this lecture, be perfectly clear on what you're trying to do. By this point, you should really not be looking for the formula for voltage division or current division, or Ohm's law. You should know them, because it's the only way that is going to help you move a little smoother into the more complicated circuit, okay? So practice. And in the next chapter, we will continue with this. All right, thank you.